Welcome back, everyone. In this lecture, we're going to explain how face detection works with the Viola-Jones algorithm with Haar cascades. So we're going to explore face detection using Haar cascades, which is a key component of the Viola-Jones object detection framework. And if you're interested in the Wikipedia article on this general topic, just look up Viola-Jones object detection framework and it'll explain the process. We've also linked as a resource the original paper, which I really encourage you to read. It's a really well-written paper. Now keep in mind, what we're covering here is face detection, not face recognition. We're going to be able to very quickly detect if a face is in an image and actually locate it. However, we won't really know whose face it belongs to. We'll just be able to say, yes, that is a face. We would need a really large data set and deep learning for actual facial recognition, being able to not only detect a face, but then say it belongs to, for example, Jose. So right now, we're keeping things simple and just talking about face detection. This arose in 2001 with Paul Viola and Michael Jones when they published their method of face detection based on the really simple concept of just analyzing a few key features. And what's really cool is they also came up with this idea of pre-computing an integral image to save time on calculations to actually find these features. So let's first understand the main feature types that Viola and Jones proposed, how we can actually calculate them, and then how we can use an integral image to really speed up that computational process. So the main feature types are edge features, where you have white against black, either in horizontal or vertical directions. And then you also have line features. Again, here we have dark with white on the sides, horizontal or vertical. And then you also have 4 rectangle features that look like this. Now, each feature is a single value obtained by subtracting the sum of pixels under the white rectangle from the sum of pixels under the black rectangle. And that would be specifically for the edge example. So realistically, our images aren't going to be perfect edges or lines. We're not going to have a perfect 0 to 1 edge. So let's see what that would actually look like. As far as calculating these features, if you have a perfect edge, such as on the left-hand side, what you're going to do is take the average in the dark region and then subtract it from the average in the light region. And for a perfect edge, that would be 1 minus 0, so 1. But for our realistic example, we'll have something that looks more like this on the right-hand side. So let's go ahead and explore the calculation. So the closer the result is to 1, the better the feature. If we actually explore the calculation for our more realistic image on the right-hand side, we can kind of tell there's an edge there. So what we end up doing is we first sum the dark region and then sum the light region. Then we take the average of them and we calculate the average to be 0.81 for the dark region and then 0.15 for the lighter region, which means their overall delta is going to be 0.8125 minus 0.15, which is equal to 0.6625. And recall that if this was absolutely perfect, the score would be 1. So the closer we are to 1, then the better the actual feature. And you can then decide on a threshold value to essentially throw away this feature and say that it didn't pass, it didn't have this feature, or that it did pass. So we could say something like above a 0.5, there is an edge there. Now, keep in mind, calculating those sums for the entire image would be computationally expensive because you'd basically have to check for every single possibility of every feature that you have in your set. So what the Viola-Jones algorithm does is it solves this by using the integral image, and this results in an order 1 running time of the algorithm. So it's really quite clever what they did here. So what you do is you pre-calculate an integral image, which is also known as a summed area table. Over here on the left-hand side, we have our original image and the original pixel values. Over here on the right-hand side, we have the summed area table or the integral image. The way you calculate this integral image is actually pretty straightforward. All you do is you go along these pixel values and then you sum them up. So for example, I have 31 here, so I have 31 here. Then my next value is 33, which is just the sum of 31 plus 2. Then if I want to keep going, then I add 4 to that. So 33 plus 4 is then 37. If I add 33 to 37, then I get 70, and so on. And what that allows us to do is it allows us to quickly calculate the sum of any rectangle on this actual image. So we can see here, as we go along, to sum up a sub-rectangle of its values from the original image, each colored spot highlights the sum inside the rectangle of that color, which is essentially just the bottom right-hand corner of that particular rectangle. So notice if I wanted to take the sum of this red rectangle here, which is 3 by 2, then I just need to locate its bottom right-hand corner in reference to the top left. So that sum is 101. And if I actually want to then perform calculations, such as subtracting a light region from a dark region, I'd be able to do it really fast if I had access to this integral table, which is why we pre-calculated beforehand. So this allows the algorithm to actually run very, very fast. Okay, so let's go ahead and move along. So after that, the algorithm also saves time by going through a cascade of classifiers, which are essentially the features. And this means we're going to treat the image to a series or a cascade of classifiers based off the simple features shown earlier, those edges and lines. Once an image fails a classifier, we can stop attempting to try to detect a face there. A common misconception behind face detection, specifically with this algorithm, is that the algorithm is slowly scanning the entire image looking for a face. That would actually be really inefficient. Instead, we're passing this cascade of classifiers. So let's work through a very simple example. First, what we need is a person looking front towards the camera. They can be looking slightly off front, but more or less they should be recognizable from the front of their face. That's what this algorithm was trained to do. So once we have that, we turn it into a grayscale image because for our use case, we're only really interested in light versus dark regions of features. So we just need the grayscale image. Then we begin in our search for the Haar cascade features. So what we do here is we start with one of the very first features. And I believe one of the very first ones that's searched for is the indication between the eyes and the cheeks. So we can see that the eyes will probably be darker than the light cheek region. So that means we have this first feature and we scan the image for it and see if it passes this test. If it doesn't pass this feature right away, so if the image were to fail for the search of this particular feature, then we can quickly say that there is no face there. We wouldn't have to search the other thousands of features. Instead, we just have this cascade or series of features, otherwise known as classifiers, to classify whether or not we have a face there. Now, if that one passed, then we search for the next classifier or feature, which is usually, I think, the bridge of the nose. And this just keeps going and going until you pass the majority of them. And you can have some sort of threshold as far as what you indicate as a feature pass or a classifier pass. So again, you continue this, maybe you do eyebrows, you do the mouth, and so on, just using these really simple ideas of edge features and line features. Until the algorithm decides, yes, I've detected a face here because it kept passing all these classifiers. Now, theoretically, this approach can be used for a variety of objects or detections, not just faces. For example, we'll also work with a pre-trained eye detector. The downside to this algorithm is that you would actually need a very large data set in order to create your own features or classifiers. However, luckily, many pre-trained sets of features already exist, so we'll be able to use pre-trained classifiers. OpenCV comes with a lot of these pre-trained XML files for various Haar cascades. Later on in the deep learning section of the course, we're going to see how to create our own classification algorithms for any distinct group of images. So because this actual algorithm requires such huge data sets, it's a little more efficient to show you how to create your own recognition classifiers and object detection classifiers using deep learning instead of trying to build out your own Haar cascades. So instead, we'll be using pre-trained Haar cascades for this section of the course, but later on we will show you how to train on your own images. Okay, so we've placed pre-trained XML files in the data folder, and you're also going to be using a pre-trained file for your upcoming project assessment, which is a really cool project. I'm super excited for it. But first, let's explore how to use facial detection with OpenCV and these pre-trained XML files. I'll see you in the next lecture where we actually open Jupyter and get started. Images of some Nobel Peace Prize winners. So we have Dennis here. And welcome back. In this lecture, we're actually going to implement the theory and ideas we talked about in the previous lecture concerning face detection, and we'll show you how to implement them with OpenCV and Python. Let's get started. Okay, here I am at the Jupyter Notebook. Go ahead and do the imports of CV2, NumPy, and Matplotlib if you haven't done so already. And what we're going to do is upload a couple of images that I've downloaded for you in the data folder. And two of the images are just images of some Nobel Peace Prize winners. So we have Dennis here and Nadia. Those are the latest Nobel Peace Prize winners from this filming. And keep in mind that one of these images, specifically the Dennis image, this is a more artistic portrait, so it is a photograph of him, but you can see that he has kind of a glow around his face, and it looks like the corners are darker than they would naturally be. And that's because some sort of photographer has edited this image, and it's a really great photo of him, but we'll see that this sort of editing will actually cause us some issues later on when we try to detect his eyes. We'll have no problem detecting his face. It's a great photo for that. It's just his eyes will give us a little bit of trouble because of how dark the whiteness around his eyes is due to the editing in this photograph. For Nadia's photo, this is just a natural photo of her, so this will work out nicely. And then we'll also detect a group face photo. We actually won't be using this specific image, but we will be using an image from the famous Solvay conference, which was in 1912. And this is actually a really famous conference. We'll be using this photo right here of all these photos here, or all the faces here. And you notice some of them aren't exactly looking directly at camera, but we'll still be able to detect those. So let's get started. We're going to upload all those images, and we're going to upload them in grayscale. So we'll say Nadia is equal to CV2 imread data / and if you just start typing capital N, you should see that appear, and then pass in a 0 there. And then Dennis, we'll also upload him and say CV2 image read data, then we'll pass in Dennis, also grayscale, and then finally the Solvay conference photo, we'll say CV2 image read, and inside the data folder there should be a Solvay conference.jpg, and upload that. So let's take a quick look at each of these images. So this is Nadia, and let's make that CMAP grayscale. There we go. So that's the Nadia image. Here's the Dennis image, and then here is the Solvay image. All right. So what we need to do is we first need to actually create the classifier and pass in the XML classifier. Luckily, OpenCV comes with these pre-trained Cascade files, and we've relocated the XML files for you in your own data folder. So in the same data folder, if you take a look at it by expanding here into data, we have these two Cascade folders. Underneath Har Cascades, we actually have quite a bit of Har Cascade files that you can play around with. Later on, we'll be using this license one for your project. So the first step is to, once you have that pre-trained XML file, you call CV2 Cascade classifier, and then we're going to call data in the Har Cascades folder, and the one we're going to be using is Har Cascade, and it's called frontal face default. So notice there's ones for like eye, frontal cat face, lots of important stuff here, and then the one we're looking for is frontal face _ default.xml. So we just need to pass that in, and then we need to actually assign it to an object. So we're going to say face cascade is equal to this cascade classifier. And this is essentially a list of around 6,000 classifiers, essentially features, that are going to be passed through the image to see if it fits all those features, and that would be an indication that there should be a face there. Let's create a quick function to actually functionalize the way this face cascade works, and then we can actually then draw a rectangle. So we'll say def detect _ face, pass in the image, and then we will say face image is equal to a copy of that image. And what happens is when you actually call face cascade, there's a detect multi-scale method on it, and then you just pass in the face image that you want to try to detect a face in, and this will return back an object that you can then use for drawing rectangles. So we'll say face recs or face rectangles, whatever you want to call it, and these are essentially just the X and Y position plus the width and height of the rectangle. So we say for X, Y, WH, so for the X and Y of the top left corner plus the width and height in face rectangles, go ahead and then just create this rectangle. So we'll say cv2.rectangle, pass in the face image, pass in the left point, top left is X and Y, and then the bottom right is going to be that X plus the width, and then that Y plus the height. And since we're dealing with grayscale, we're just going to make the actual rectangle white, so 255 for all those color channels, or you can just pass in 255 since we're not dealing with really color channels there. And let's give it a thickness of 10. And then we're going to return the updated face image. So you should be able to just write in 255 here. Don't worry about those color channels. So we have detect face, and then let's go ahead and check out the result. So let's run detect face on Dennis, and then plt imshow.result with a gray mapping. And here we were able to successfully detect his face. So let's run this again, but now we'll run it with Nadia. Run that, and then we get to see Nadia's face. Now, let's try running this on the Solvay conference. So the Solvay conference, remember, has multiple faces. In fact, it has a lot of them, and some of them aren't even looking directly at the camera. So we're going to try saying detect face, Solvay, and then view that result. So you'll notice right off the bat that some of these things that it's detecting aren't faces, and actually this may be a gargoyle or something on that building, so that may be wrong, but we can see here we're also detecting double faces. So what we're going to do is we're going to add a few parameters, specifically scale factor and minimum neighbors. Let me copy and paste this detect face function, and then what we're going to do is call this adjusted underscore detect face. And we're going to add in a few parameters to this detect multiscale. And if you do shift tab here, you can see that we have this scale factor and this minimum neighbors that we can end up adjusting. The scale factor is a parameter specifying how much the image size is reduced at each image scale. And then the minimum neighbors is the parameter specifying how many neighbors each candidate rectangle should have to retain it. So what happens is, as you actually perform some of these classifiers, you'll end up having multiple rectangles detecting a face. And if multiple rectangles are near the same area or have a minimum number of neighbors, then we decide that is where the face is. So we can go ahead and play with some of these parameters. I'm going to use a couple of defaults that worked well for me, but a lot of times this is just experimentation. We're going to say the scale factor here is equal to 1.2, and that the minimum neighbors is equal to 5. And then we're going to run the adjusted face. So we'll say result is equal to adjusted detect face on the Solvay image. And now let's see the result of this. We'll say results, CMAP is equal to gray. And when you run this, you see now you get a much better and clearer detection of the actual faces. The only caveat being that now this person that was looking sideways, you're no longer able to detect his face. So it's kind of a trade-off. It's a trade-off between detecting too many faces, so this little thing right here, and then detecting a face twice over this man, or missing out on some faces that aren't looking directly at the camera. And you can begin to adjust these scale factors and minimum neighbors to see if you can find a better balance between the two. Just keep in mind when you have an image with lots of faces and people looking in different directions, some XML file that's specifically made for a frontal face may not work very well. Now let's check out the eye cascade file. So we'll say eye cascade is equal to CV2, call cascade classifier again, and inside the data folder, under the har cascades, we're going to look for har cascade underscore eye. And then in a really similar fashion, I'm just going to copy and paste the original detect face function, except we'll then call it detect eyes. So we'll say detect eyes, and everything else can be the same, except we'll say this is, instead of face rectangles, these are eye rectangles now. And then instead of calling face cascade, we will call the eye cascade, and then change this to eyes rectangles. Everything else is pretty much the same. What's going to happen is this is actually going to return 2 rectangles if it finds a set of eyes. And then we're going to run that and check the result on detect eyes. And we'll first do it on Nadia and show the result. plt imshow results CMAP is equal to gray. Run that. And here we were able to detect the eyes, but notice it actually detected her nostril as well, thinking it was an eye. So you may have to also then adjust this multiscale the same way we adjusted here for scale factors and minimum neighbors. So what you could do is just even try copying and pasting this and see if that helps. So you can try copying and pasting those scale factors and then minimum neighbors, run that, and you'll notice it will actually then clean up the nostril it found. So it could have thought maybe it has another set of eyes somewhere in the image, maybe they thought there was 2 people, but these actually aren't sophisticated enough to return back only pairs of eyes, because maybe someone's winking or something. Okay, so we were able to fix that issue, but now let's take a look at what happens when we search Dennis's face for eyes. we'll say result is equal to detect eyes on Dennis, and then I'm going to say PLT imshow result CMAP is equal to gray. And what happens is, whoops, if we spell that right, result, you don't get any rectangles around Dennis's eyes. And that's because if we look at the original photograph here where I got this from, you'll notice that the whites of his eyes are actually really dark. In fact, they're almost the same color as some parts of his skin. And some parts of his skin, because of the editing that the photographer did on this photo, they're actually lighter than the whites of his eyes. Versus if we look at Nadia, the whites of her eyes are really quite distinct from the rest of her face. And that's one of the main features that this cascade is looking for. So we would have to find an unedited photo of Dennis here in order to actually detect his eyes correctly. And this is kind of a particular photo that it won't work with. And it's really just because of the editing done on this photo due to some contrast, and they add a little bit of vignette here to make it look a little darker. It tinted his eyes color, and you can also see his pupils are actually quite large as well here. They're dilated in this photo. So lots of stuff going on here that caused us to not detect his eyes, even though as humans we can clearly see where his eyes are. So that's one of the tricks of working with these sort of cascade files. Now, as you're probably wondering, how can you actually do this with video? Well, with video, it's pretty straightforward. All we need to do is start capturing video with CV2, video capture, and I'm going to capture this straight from my camera. So we'll say video capture 0. And then what we're going to do is say while true, say RET and frame is equal to cap read 0. And then say frame is equal to, and we're just going to run detect face on the frame. So essentially, anything you do on a single image, you can do on a single frame. And then we will say CV2 image show video face detect, and then we'll show that frame. And I will make a wait key here. I'm going to say C is equal to CV2 wait key 1, and then if, let's actually make this K, if K is equal to 27, go ahead and break. So if I hit break, or excuse me, if I hit escape key, it'll stop recording. Then as always, we want to release the camera and then say CV2 destroy all windows. So let's run this. And let me bring up the actual streaming. So there I am, and now I'm going to look basically more directly into the camera, and you can see that it's able to find me. In fact, let me pick up the camera here, and now I'm going to put my hand above. You can see it's not now no longer working that well. In fact, it thinks my hand is a face, and maybe if I can trick it. No, that didn't work. But if I'm clearly looking at the camera, if I'm looking frontal face, it should have no problem, even if I move my face, detecting it. So that's really what it's designed to do. It's designed to just quickly have a facial recognition for someone looking more or less probably within like 45 degrees of frontal. Now if I start going too much to the side, you'll notice that it no longer finds me. Okay. So that's it for object detection with cascade files. What we're going to do is expand on this and actually have you perform a project that uses a pre-built cascade file in order to blur licenses. Okay, thanks, and we'll see you at